Okay, now we'll start our next alkaloid. Alkaloids derived from the tryptophan. So this one we will start today. So in alkaloids, tryptophan alkaloids derived from, that means it contains the main nucleus is indole. So these alkaloids, biggest single class of alkaloid, it has more than 1,500 known alkaloids present in under this indole type of alkaloids. So indole alkaloids comes from tryptophan, which originates from the shikimic acid pathway. Many are of mixed origin using geraniol or terpenes as an precursor. Okay, so we'll see now. L-tryptophan is an aromatic amino acid containing an indole ring system having its origin in the shikimate pathway via anthracanic acid. We'll see on next slide how we can synthesize the tryptophan from the anthracanic acid via shikimic acid pathway. It acts as a precursor of a wide range of indole alkaloids, but there is also definite proof that major rearrangement reactions can convert the indole ring system into a quinoline ring, thus increasing further the ability of this amino acid to act as an alkaloid precursor. We'll see now how to synthesize tryptophan from the anthracanic acid. So we can synthesize tryptophan here. You can see. Okay, so tryptophan is amino acid. Okay, and this amino acid we can synthesize from the anthracanic acid. Okay, but this anthracanic acid, that one is getting synthesized via biosynthetic pathway from the chorismic acid. Okay, so this is the path of synthesis of anthracanic acid first in via biochemical pathway. Okay, so everything is all this synthesis they do occur in living organisms, and once anthracanic acid synthesized, we can synthesize tryptophan from anthracanic acid. So we'll see in detail how the tryptophan is getting synthesized from the anthracanic acid via biosynthesis pathway. So here is the schematic representation of synthesis of tryptophan with from the anthracanic acid. So here is the anthracanic acid, okay, and phosphoribosyl pyrophosphate. With the help of this enzyme, phosphoribosyl pyrophosphate, okay, we can do the different reactions of synthesis of tryptophan. So here is the mechanistic way, biosynthetic pathway. Nucleophilic nitrogen attacks on this phosphoribosyl pyrophosphate. Then at the end, in the beginning, there is a formation of imine. Imine undergoes tautomer. Imine is nothing but the C double bond N bond. Imine undergoes tautomer to make enamine. Okay, enamine undergoes again tautomerism. It gives the enol. Okay, so from enol to keto. Okay, there is tautomerism in between enol form to keto form, and from keto form there is decarboxylation and elimination of water molecule. Okay, with the cyclization of this molecule of this open chain to form our indole nucleus. Okay, so once we got indole, so reverse aldol via reverse aldol reaction, we can get indole, and indole on treatment on reaction with or with reaction serine in presence of PLP. Finally, we will get tryptophan as our precursor for the synthesis of different alkaloids. Okay, so we'll see now in our syllabus which alkaloids comes under this topic. Alkaloids are from the tryptophan, so we have to see different alkaloids like uh, psilocin, hermine. Okay, so azomycin, yohimbine, cinchonine, quinidine, camptothecin, lysergic acid. Okay, so all these alkaloids we'll see how we can synthesize from the tryptophan. So this is our um, uh, this is our motto today, is to see the synthesis of different alkaloids. alkaloids from the tryptophan. Okay, so here is the tryptophan synthesis schematic pathway. So once we got tryptophan synthesized, we can go for different alkaloids. Okay, so here simple carboryl alkaloids. Now we will go for beta carbolyl alkaloids. So position second of the indole system is nucleophilic due to the adjacent nitrogen atom. Okay, position second is of indole system is nucleophilic due to the nitrogen atom. So now you can pay attention. At third position we got this substituent, okay, of tryptophan. Second position of this tryptophan is empty, and this we can utilize this second position of this indole nucleus to form the beta carbolin type alkaloids. Okay, so these beta carbolin alkaloids we can synthesize by this second, what is the empty second position in the indole system, which is nucleophilic due to the adjacent nitrogen atom, and can participate in Manich or Pictet-Spengler type reaction, attacking an imine generated from tryptamine and aldehyde, okay, or keto acid. So now we will go to synthesize the beta carbolin first. Beta carbolin we can synthesize from by reaction of the tryptophan with any aldehyde. Okay, so we'll see how to synthesize the beta carbolin type alkaloids. Okay, so first we will see the how to synthesize this beta carbolin. So pay attention here, tryptophan moiety we have taken molecule amino acid. Okay, so this is amino acid. Now this second position is empty, and which acts as a nucleophile. Okay. So we will utilize this second position to form this beta carbolin alkaloid. So this beta carbolin, this tryptophan react with aldehyde from an amino acid, aldehyde from an amino acid. So how we will see now how this tryptophan will react with aldehyde. So tryptophan, that one is when there is a reaction, there is elimination of water molecule from this amino group and aldehyde group, and there is a formation of C double bond N bond. Okay, so this undergoes further cyclization, and we will get the beta carbolin. Okay, so these things, all this mechanism, it involves the Manish type reaction as well as Pictet-Spengler type reaction. Okay, attacking an imine generated from the tryptamine. So imine generation we have seen. So aromaticity of this tryptamine is restored by subsequent loss of the C2 proton. Okay, C second position will loss subsequently to restore the aromaticity. It should be noted that the analogous chemical reaction actually involves nucleophilic attack from C3, and then subsequent rearrangement occurs to give bonding at C2. This type of process does not appear to participate in biosynthetic pathway. We'll see now again one more slide for this mechanism. Okay, beta carbolin synthesis from the tryptamine. Okay, so here is tryptophan. We are going to react with aldehyde. First there is a imine formation using aldehyde. So here we got imine formation. Now see, pay attention here. Second position is nucleophilic. How second position is getting nucleophile? Pay attention by shifting of this lone pair which is present on nitrogen atom. Okay, so this pyral ring is aromatic. So this lone pair is shifting. The carbon-carbon double bond from aromatic benzene ring is shifted in between here, and this carbon-carbon double bond acts as a nucleophile. Okay, to it will attack over on this C double bond N imine bond, C double bond N, and this is Manich like reaction. Okay, alpha carbon acts as a nucleophile. So this is alpha carbon atom. Okay, so this is alpha carbon atom, and it attacks on this carbon nitrogen double bond. So lone pair shifted on the nitrogen atom. Okay, and in this way we can form a new carbon carbon bond in this way for the cyclation. Now we have to look after for this retention of this aromaticity. Okay, so with the elimination of this proton from this moiety, tautomerism to restore, it can restore the aromaticity. So we got here the restoration of this aromaticity. This compound on oxidation, okay, in oxidation it gives the formation of this carbon carbon double bond. Okay, and in this way this is our final molecule of the beta carbolene. Okay, so here the structure he has given, and lot so many alkaloids now we are going to synthesize from this beta carbolene, which involves, or we can say some alkaloids they contain this beta carbolene as a basic moiety. So pay attention how the numbering has been given to this beta carbolene compound.